So we're going to go ahead and talk about the state of ketosis today. And first we're going to start out with the physiology of ketosis, and then we'll go ahead and move into the biochemistry of ketosis and see how ketone bodies are made in your liver and how they work. So we'll start with the definition of ketosis. All right. And ketosis is the state of high blood ketone body concentration. I'm just going to use these brackets for concentration. All right? So blood ketone body concentration. All right? And that's usually due to high fat metabolism. So when your body begins to run out of glucose, and this typically happens in a state of fasting or more severely in a state of starvation, and your blood glucose levels drop and your glycogen levels drop, which are your storage form of glucose in tissues such as your muscle or your liver, and you don't have enough blood glucose to supply certain tissues like your brain and red blood cells with constant energy, you will start burning fat to provide energy to your body, and fat can go through the processes of the tricarboxylic acid or Krebs cycle and the electron transport chain to give you ATP energy. And when you start burning high levels of fat, your liver catches wind of this. And your liver will convert these fatty acids into ketone bodies. All right? And then these ketone bodies can be used for energy by your brain because they are one of the few molecules that can cross the blood-brain barrier. All right? And then they can provide you with energy. And there's some benefits and some downsides to ketosis. One of the benefits is that it's a perpetual state of fat burning, so it's one way to naturally burn fat off your body. But some of the downsides are, one, that glucose is the primary source of preferred fuel for the brain. All right? So, if we don't have glucose and we switch to ketone bodies, your brain will do that and use them for energy, but it won't prefer it. And two, it can lead to acidosis, which is a lowering of your body's pH, which is not ideal. All right? Our body works at a very specific pH of about 7 to 7.4, and we want to keep that. If we go to a state of acidosis, our body can start having problems due to a lowering of the internal pH of the body, because one particular ketone body in particular is quite acidic. And we'll get into that as we get into the biochemistry. All right, so that's some of the physiology of ketosis and how it works and why it happens. And now let's look at the biochemistry of it. And before we get into the exact biochemistry, we have to provide some background on fats. All right, remember that we store fats as a triglyceride. All right, we store fats as, or I should say as triglycerides. All right, so there's one triglyceride, which is a glycerol backbone with 3 fatty acids. All right, and a fatty acid has the first carbon with a carbonyl group on there, but is essentially just a long hydrocarbon chain. 1, 2, 3, 4, 5, 6. That'll work. They're usually even numbered. And the reason that they're even numbered, and we'll draw some H's on here to show that all these bonds go to H's, go to hydrogens. The reason they're even numbered is because when we break these fats apart for energy in the mitochondria through a process that we call beta oxidation, we're going to break them into 2 carbon units. All right? And one of these carbons will get a carbonyl group on them. And this becomes an acetyl group. All right? So we have an acetyl group, and we're going to attach these acetyl groups to molecules called CoA, or coenzyme A. And coenzyme A is a big molecule that equals an adenosine, which is a molecule that we see involved in ATP and also in DNA. We see it in a lot of places. And a pantothenic acid, as well as a sulfur with a hydrogen. This is called a thiol group, and pantothenic acid is actually vitamin B5 as well. So that's CoA, that's a pretty big molecule. We're going to stick that onto an acetyl group that we got from the fatty acid, and this gives us acetyl-CoA. All right? And acetyl-CoA is the molecule that you enter into the Krebs cycle with from fat so that you can start burning that fat for energy. Okay, and that's also where we're going to start with the biochemistry of how ketone bodies are made. So when you start making a lot of acetyl-CoA, you eventually will start to run out of free CoA to add to the acetyl groups, and that becomes an issue. So in order to fix that, your liver, will start making ketone bodies as a way to free up that CoA, as well as to provide a molecule to give your brain energy that can cross the blood-brain barrier. So let's see how it does that. In the mitochondria of the liver cells, we're going to start with 2 acetyl-CoAs. All right, 2 acetyl-CoA goes to, and this uses an enzyme called thiolase, goes to what's called acetyl-CoA plus a free CoA. All right, so let's quickly draw these molecules and see what they look like right under here. That's acetyl-CoA, and this is acetyl-CoA. All right, CH2, and there's our CoA group right there. All right. Now we're going to take acetyl-CoA and we're going to add to it another CoA group. All right. Plus another acetyl-CoA, and this is going to give us a molecule with a very long name, but we're just going to call it HMG-CoA, and then we also get another free CoA here, and these CoAs are very important because they can be sent back for more beta oxidation. All right. Now HMG-CoA can take 2 pathways in the liver cells. In the cytosol, it can go to cholesterol. HMG-CoA can go to cholesterol. Maybe a process or a chemical pathway that we'll talk about in another video. And in the mitochondria, it can be made into ketone bodies. We'll see how that works. I should probably spell that right. Goes into ketone bodies. Ketone bodies. All right, so let's see how that happens. All right. So we'll take HMG-CoA and we're going to add another acetyl-CoA to it, and we'll do that quickly. So HMG-CoA plus acetyl-CoA gives us, and I'm just going to draw this arrow down here, acetoacetate plus acetyl-CoA plus another free CoA. All right? And acetoacetate is our first of 3 ketone bodies. All right? Now from there we can make another ketone body called acetone, and we do that by splitting off a CO2 group. All right? Or we can take acetoacetate to the 3rd ketone body called beta hydroxybutyric acid. And beta hydroxybutyric acid, and we do that by using NADH going to NAD+. Okay, so this is a reducing agent. And this is not technically a ketone body. It's technically a carboxylic acid, and it's the ketone body. We group it in with them. It's the ketone body that can lead to acidosis because it is an acid. All right. But here are your 3 ketone bodies that your liver can make to put you in the state of ketosis.